Aspartic acid is one of the two acidic amino acids, which means that the R group on aspartic acid has carboxylic acid attached to it. If you don't remember what the R group of an amino acid is or how the alpha carbon situation works, check out the video linked in the description below. If we're looking at it, this is the overall structure. There's only one carbon on any amino acid that has a chiral carbon, which means there are 1, 2, 3, 4 different attachments on the one carbon itself. Every other carbon has 2 similar attachments, so none of those are considered chiral. The one chiral carbon is the one that has a hydrogen attached to it. It also has an amino group attached to it in blue. It also has a carboxylic acid group attached to it, which is this 2 reds. Those look like those are oxygens. And then it also has whatever is the R group. If you ever see this written out, you'll normally see it something like this, where you'll have the amino group on one side, the carboxylic acid on the other side, the R group pointing down, and then you can't see the hydrogen because it's in the back. And that's how you have the little dashes if this is written out. Aspartic acid can be in 2 forms, a D form or an L form. Aside from the L versus D situation, let's also talk about the R group itself. So you'll see the R group, the R group has the carbon that was attached to the main amino acid taken off, and that carbon has 2 hydrogens attached to it. And then that one carbon is attached to another carboxylic acid, where you have a double bonded oxygen as well as an OH group. So because there's one carbon that's connecting it to the overall chiral carbon, this carboxylic acid that only has one carbon is the COOH attached to the chiral carbon is going to be more acidic than this carboxylic acid that has this extra carbon attached to it. So if we're talking protonation or deprotonation, aka adding or removing a hydrogen, this is the most protonated form that it can be. Everywhere there is a lone pair of electrons, that lone pair is filled in with some kind of hydrogen. And as you increase the pH, aka decrease the number of hydrogens that are around, these hydrogens are going to be less likely to stay bound to this and start to escape and go to other molecules that need the hydrogens more. In any amino acid, the first hydrogen that's going to be lost from this amino acid structure is going to be one on the carboxylic acid that is attached to the chiral carbon. And this also allows for the peptide bond to be made, which is also discussed in the video linked below. At the lowest pH, the first hydrogen that's going to be lost is going to be lost from this oxygen, carboxylic acid attached to the main chiral carbon. The second hydrogen that's going to be lost from this amino acid is going to come from this carboxylic acid, which is the R group on the alpha carbon. So this hydrogen is going to be the second one that's going to be lost. And it is lost when the pH is about 3.9. If you're going from a really low pH up to 3.9, the first one that's lost was this hydrogen. The second one that's lost at 3.9 will be this hydrogen. So now this is going to carry a negative charge. This nitrogen has an extra hydrogen added to it. It shouldn't have 4 bonds. It should only have 3 and then an extra lone pair. But that lone pair is now added to a hydrogen. So this is positively charged. So we've got a negative charge and a positive charge on the same molecule, which is called a zwitterion, or when you have 2 opposite charges on the same molecule. But then, because you have a negative charge, because this oxygen is now a lone pair, it's going to make it a -1 charge. And this is going to continue being this -1 charge overall until the pH gets to about 9 something. And then finally, around 9 something, one of the hydrogens from this nitrogen is going to be lost, and that nitrogen gains its lone pair back. So at this point, now it's -2 charge because it's -1, -1, and then 0. So -2, and then 0 is overall -2. But this happens way above the pH of your body, which is the physiologic pH, or about 7.4. At 7.4, this nitrogen is still going to have the hydrogen attached to it. And so at any physiologic pH, aspartic acid is going to have an overall charge of -1. And because this overall has a charge of -1, this is not going to be called aspartic acid. This isn't a carboxylic acid anymore. It's an COO negative. This is an 8 ending. So this is going to be called aspartate, not aspartic acid. The carboxylic acid losing its extra hydrogen doesn't have anything to do with the naming of the molecule. It's solely dependent on whether or not the oxygen that's on the R group has or does not have the hydrogen attached to it. Aspartic acid, there is a hydrogen. Aspartate, no hydrogen, extra lone pair of electrons. This amino acid is not considered an essential amino acid because it can be made from other things within the body via transamination reactions, where you're moving an amino group and transferring it from one place to another. So transfer, movement, amination, amine group. So the movement of an amine group from one thing to another allows for aspartic acid to be made in the first place. You can also use the same transamination reactions to make some other amino acids that are also considered non-essential. But this amino acid is not an essential amino acid. You don't have to eat it from something in your diet. You can make this within your body using transamination.